Babbage and his engines, part 2. We're going to look at Babbage's first engine, the difference engine. It wasn't built in his lifetime. He started it, but ran out of money. In the 1980s, the Science Museum in London did build the machine. And this picture is the machine in the Science Museum, with Doron Swade, who was responsible for the project, standing beside it. So you get the sense of the size and complexity. And this photograph was taken before they'd made the printing section, which would be on the left, about where Doron is standing. The timeline here is quite important. In 1821, Babbage had finished the design. He had a set of engineering drawings. He went to the government and got some funding. And he hired an engineer, Clements, and they went out and set up a workshop and hired some of the best mechanics they could find in England. And they spent the next 10 years making parts for the engine. By 1831, they'd finished about half the 25,000 parts. They ran out of money. There was a year of arbitration, and the project was abandoned. In 1834, Babbage turned his attention to the analytical engine. This was a much more complicated engine, and by modern standards would definitely be considered a computer, even though it was entirely mechanical. And he worked on the design of that engine on and off for the rest of his life, but none of it was ever built other than a few small parts. Between 47 and 49, he went back to the difference engine design because in designing the analytical engine, he'd figured out how to do things in a better way. So he finished up with some engineering drawings for difference engine 2, and that only had about 8,000 parts. In the 1980s, when the Science Museum undertook to build the engine, it's quite obvious that they chose to build difference engine 2. In some respects, building difference engine 1 in Babbage's day was somewhat similar to building the James Webb Space Telescope. Both projects were pushing the available technology to their limits. So let's look at how difference engine 1 worked. And I was going to put together some graphics, which wouldn't be easy to do, but I found this website. It's a superb set of graphics. I've taken an extract here, but please, there's up to an hour of video on various parts of the difference engine, which I highly recommend. This is just a few minutes to get you the sense of how the main parts of the engine worked.
Babbage's difference engine number 2 contains 8 numeric storage units, each implemented by a column of gears called figure wheels. The teeth of a figure wheel encode the digit values 0 through 9. Each figure wheel has 40 teeth, representing 4 identical runs of digits, and the same digit value can be represented by any of the 4 runs. If a wheel is turned by 3 teeth, it represents the number 3. Each column contains 31 wheels mounted on a vertical axis, which together represent a 31-digit number. The least significant digit is at the bottom of the column, and the most significant digit is at the top. Negative numbers are dealt with using the tens complement method. Floating point numbers are implemented by scaling. 7 of the columns are accumulators. That is, they contain hardware for incrementing their value by the addend stored in the column to the right. Let's see how that is done. With 2 wheels, you can do simple addition. If you want to add 4 to the accumulator wheel, you turn the addend wheel 4 teeth, mesh the wheels, turn, and you get the sum of 7. A problem with this arrangement is that we have lost one of the numbers we started with. That number needs to be recovered for use in the calculation phase. So Babbage introduced a third wheel he called a sector wheel, because it has only a section of a full wheel. The sector wheel is designed so it can engage with both the accumulator and add-in wheels, only the add-in wheel, or neither wheel. The sector wheel meshes with both gears during addition and records the value of the add-end transferred from the right. It then disengages from the accumulator wheel and restores to the add-end wheel the number it started with. The figure wheels rest on a comb-like structure and rotate freely about a figure wheel axis. The sector wheels rotate freely about their own axis, resting on a lip attached to that axis. The transfer of numbers is powered by a pair of drive arms attached to the figure wheel axis. The drive arms press against nibs positioned at 90-degree intervals inside the barrel of the figure wheel. The drive arms in the add-end figure wheel are lowered during the transfer of numbers, so they engage the nibs and spin the wheel. At the same time, the drive arms are raised in the accumulator figure wheel, allowing it to be driven by the rotation of the add-end wheel via the sector wheel. The add-end drive arms are then raised above the nibs, disengaging from the add-end wheel, and the sector wheel is raised to disengage the accumulator wheel. A restoring arm on the sector wheel axis is then used to rotate the sector wheel back to its starting position, while at the same time restoring the add-end wheel's original value. To handle carry values generated during addition, Babbage designed a mechanism that causes the figure wheel above to advance one digit each time the figure wheel below passes from 9 to 0. The mechanism consists of a 3-armed carry lever, a spring-loaded warning mechanism, and a carry sensing arm. The carry mechanism works as follows. The addition of numbers is carried out first. If an accumulator wheel passes from 9 to 0 during the addition, a nib on the exterior of the accumulator wheel barrel nudges the carry lever into the warned position, which warns that a carry is still needed. The carry lever is held in the warned position by a spring-loaded detent lever that engages a V-shaped notch in the detent arm of the carry lever. After the addition, the carry mechanism is lowered into place. Each warning mechanism is sampled by a carry sensing arm, which sweeps past. If the warning is not set, the sensing arm does not engage the carry lever. If the warning is set, the sensing arm pushes on the carry lever, which rotates the next higher accumulator wheel forward by 1 tooth. After the carry sequence, the carry mechanism is raised to disengage it from the accumulator wheel, and it is reset to its unwarned position by pressing against a reset stop in preparation for the next addition. The carry sensing arms are staggered around their axis, forming a helix. Each figure wheel in a column is sampled one after the other, allowing consecutive carry values to propagate up the column of figure wheels properly.
Here are some of the parts manufactured for the Science Museum. Each of these parts could fit easily in the palm of your hand. So you can see the complexity and difficulty of manufacturing these parts even today. These, of course, were made originally entirely by hand. A friend of mine, a professional engineer and a hobbyist, made this part of the carry mechanism. Is probably the most complicated piece of the engine. And he went through the same sort of process that the contractors for the Science Museum went through. He first thought he cut it from a piece of solid brass, but couldn't find a way of holding it for making these rather complicated cuts. So he decided to make it in sections and solder the sections together. And even then, it was a particularly tedious job. So he finished up producing the parts on a hobby CNC milling machine, that's computer numerical controlled milling machine. He made them in CNC parts and then soldered them together, just like the contractor did for the Science Museum. Here's a plan from the Science Museum. It's a very close copy of an original drawing by Babbage. It shows over here 3 figure wheels, 2 sector wheels, the arms inside to turn around and pick up these nibs. And up here, we've got the carry mechanism. And this sort of thing here, in Victorian times, this wheel would notch between the different places. In other words, it steps around. And in Victorian times, they drew every step at which it could stop individually. So you get a sense of how it would have worked. I don't think that's done these days. But I'm going to zoom in on that section in blue. And we see there that the thing that the blue arrow is pointing to is a lock. When the wheel is going to be turned, the figure wheel in this case, the lock is withdrawn to the left, so the wheel will turn. When it gets to its final position, it may not be absolutely precisely in the center between 2 teeth. So the lock moves in, and the wedge shape brings the teeth exactly central. And there's got to be a bit of room to play around in gears, otherwise they won't turn. So there has to be a little bit of slack, and this lock picks up the slack and forces the wheel to the precise central position. And you can see this a bit better in this illustration here. And on the right, in the smaller picture, you'll see that there's a bit of wear in the wheel, and it's stopped, so that when the lock comes in, it hits on the end of a tooth. That will stop the machine. It will jam up. This is by design. Babbage didn't want to get erroneous results. He didn't want the lock to slip into the adjacent gear tooth. So this mechanism stopped that happening. Better to stop the machine than do something wrong. One of the problems I had with the video, it talks about 31 digits, as many sites on the web do. And I often wondered why 31 digits is most peculiar. Well, in Babbage's second engine, the analytical engine, he put an extra digit wheel, figure wheel, at the top of his columns of digits. And that was used to indicate the sign. And I believe that he did the same thing in the difference engine. So we actually had 30-digit numbers and then an extra figure wheel on top to indicate the sign. A even number meant the number below was positive, and an odd number meant the number below was negative. And I support that view because the difference engine had a printer. And we can see the printer there printing out on paper. And if you count across, you'll see there's only 30 digits printed out. The printer was very sophisticated. In addition to the paper scroll, it produced a stereotype. This is a tray filled with plaster of Paris or paper mache. and the numbers were pressed into that tray, and when it was full, it was taken out of the machine and let to set up and dry, at which point molten lead could be poured in to make a printing plate. That meant there was no typesetting and no proofreading necessary. Now, the machine was cranked by a hand, and it would be very disconcerting for the person cranking the machine if it suddenly stopped when the stereotype was full. So Babbage had designed a mechanism so that in the last turn of the machine, before this stereotype was full, a little pin will pop out of the crank, the handle the operator was using. He could sense that and then come to a nice, pleasant, smooth stop at the end of the turn. The printed pages looked a bit like this. I got this on the web, and it's supposed to have been produced by the machine in the Science Museum, but I couldn't see anywhere where the printer would print this rectangular box around. So that may be something else. But the general appearance of the page is exactly the sort of thing that the machine would have printed, with the page headings, the column headings, the bold fonts, and so on. In fact, this printer was quite remarkable. For example, it would handle lines of variable line height, and the column height had gaps for readability, and it could hold up to 4 columns, large and small font on the same page, and the line height was based on the font, and there were page headings, and line and column wrap. And you see line wrap here and column wrap here. And here's a photograph of the printing mechanism from the front. And here's a photograph from the side. Now, of the 8,000 parts in the machine, it shouldn't be a surprise now to recognize that 4,000 parts were used in the calculating section and 4,000 parts were used in the printer. To get this thing to work, Babbage produced these several drawings like this. They're large 3-foot by 4-foot drawings, and these bars indicate the timing of things, when things turn on and when things turn off, go up and down, gears engage, etc. And this was necessary to figure out the correct sequence of moving things so the engine would work. The Science Museum has in their archives, I think, about 7,000 engineering drawings, most of which are for the analytical engine, but there are several hundred for the difference engine. And in addition, there are about 10,000 sketches and about 20,000 notebook pages. In the archive are quite a few of these cardboard cutouts. Babbage could pin these onto a board and try out to see that things were lined up and would work properly. About a year before the project was cancelled, Babbage and his engineer Clement took a sample of parts, about a couple of thousand parts, and they put together this model here. We'd call it a prototype, and I'm going to call it a prototype, although Babbage didn't use that term. And in that prototype, it's 3 columns. It'll do the method of differences in a simple example, and I think it's got 9 digits. And this was the very, very first time a machine had been built that you could dial in numbers by turning these wheels here by hand to set it up. Pull the crank, and it would add the numbers together. And this was an automatic addition, meaning that if there was a carry, the carry would be carried out automatically. It was the very first automatic adding machine. How did the Victorians make all these parts to this precision, necessary precision? Well, they used verniers, a vernier caliper. This is mine, it's a hobby one. It's very similar to the sort they'd have had in Victorian times. I think this one, when I bought it, probably about $50–60 today, US dollars. And it will measure to 1/1000th of an inch. But mine isn't a calibrated caliper. If I wanted a calibrated one, I'd have to spend at least 10 times as much. But it's fairly good, and it's probably maybe within 1/1000th, probably within 2/1000th. The problem is, how long is an inch? And this was a problem they had in Babbage's day, because they would have used calipers like this, but there was no standard inch. Now, they were expensive, far more expensive than mine, so not every worker would have one. Clement, as the boss, would have had one, and most likely Whitworth, one of the employees of Clement. He was very interested in precision and would have most likely had his own. And they'd have both been very good instruments for the time. But if you put them side by side, they wouldn't agree, because an inch is not the same for Clement as it is for Whitworth. So you couldn't make uniform things in a workshop using calipers. What they did was the best workmen would make up a gauge. So let's say they were making, maybe the sector wheels, and they needed 248 of them, 31 digits by 8 columns. So you've got 248. So several workmen would have worked on the sector wheel, and they'd have made up gauges for all the important dimensions. These gauges would have been made from one master caliber, probably Clement, you see, he was the boss. So every gauge would be very carefully made to the correct size according to that one set of calipers. They could then distribute the gauges around the workshop so individual workers could have their own gauge, and they could leave them on the workbench. The calipers were far too valuable and sensitive to leave lying around on a workbench. The idea then was that the workman would make a part and file it down till it just slipped into the gauge. It had to be a little bit of friction, no slack, but not enough that it was stiff. And if you did it very carefully, you could get well within 1/1000th of an inch. And the gauge itself was within about 1/1000th of an inch of the calipers. So they could manufacture lots of parts that were identical and would fit together. If you want to know how a vernier caliper works, there's an excellent website here. You can download and print out a page, cut it out, glue it together, and you've got your own vernier caliper. It's obviously not as precise as a metal one, but you'll get the idea and see exactly how it works. Now, my friend John, a professional engineer and also a hobbyist, he said, at the time of Babbage, a machined part usually would be made to the final size using hand tools. He said, it's interesting that 100 years after Babbage, the machined parts of the Rolls-Royce Merlin engines were still filed to fit. It was only after the Americans started to make them on production lines where the tolerances tightened so that parts became readily interchangeable. Right top, there are some nuts and bolts, the way I'd buy them from my local hardware store. At the bottom are 2 nuts and bolts, the way Babbage would get them. Babbage would have to go to a workshop and order 2 bolts of whatever the size was, and he'd order nuts to fit. And the nuts to fit was a magic term used in all Victorian contracts. And it was literally that, the nuts would be made to fit. And heavens help a poor apprentice, whoever got the nuts mixed up, because even if these 2 bolts came from the same workshop, the probability is that a nut from the bolt on the right wouldn't fit the bolt on the left. There was no standardization. Joseph Whitworth, who was hired by Clement, he was party to some discussions with Babbage and Clement about standardization. And when the project was abandoned and cancelled, he went off, set up his own workshop, and was very successful. And he established a standard thread and we have the British Standard Whitworth thread. And for that reason, Whitworth became a Fellow of the Royal Society, and he had Sir in front of his name. Said that Babbage made Clements, Clements made Whitworth, and Whitworth made the threads. Now, Doron Swade was head of conservation for the computing section at the Science Museum in London. And in the early 80s, he proposed building the complete engine for the bicentennial of Babbage's birth, which would have been December 1991. The project was proposed, and the first question, of course, was, could the Victorians have actually built this engine? Well, we know that Clement had manufactured 12,000 parts, which is most of the computing section, and at that point the money ran out. And we know that Clement and Babbage assembled about a seventh of these parts to make that prototype, which is in the Science Museum today. It's a beautiful piece of work, and it still works. Most of the remaining parts were melted down, but some survived. So Doron Swade sent some of those parts over to Imperial College London, where they were analysed to determine the type of material. It was found to be gunmetal, which is a type of tough brass. It was readily available in the 1980s, and it's still readily available today. The Science Museum staff also measured parts that were built by Clement and others in the workshop. And they found that all the parts were within 2/1000ths of an inch of the specified dimensions. This is very good for handwork. These people that Clement hired knew what they're doing. They weren't rushing, and they produced an excellent product. Here we see the team at the Science Museum. And on the left is Alan Bromley. He was professor of computing science at Sydney in Australia. And he was spending a year at the Science Museum going through Babbage's papers, in particular, papers for the analytical engine. But he did spend some time on the difference engine and was very helpful to the rest of the team. The drawings were prepared by a specialist firm, and then the manufacturing was tendered. This is the tendering for the 8,000 parts. Now, at the time, Margaret Thatcher was Prime Minister of Britain, and she was requiring privatization. And the Science Museum at that time didn't have any expertise in tendering large projects. So there are administrative delays as they were figuring out how to go about that. But eventually manufacturing started. There were further delays and problems with funding. And Doron Swade spent most of his time rushing around trying to find money. And then, at a critical point, the company that was running the project went bankrupt. Fortunately, the Science Museum hired the project manager from that company, which was critical because it maintained continuity. If that hadn't happened, the project was unlikely to be finished. The assembly was done in the Science Museum in public. And the two gentlemen here worked quite a while to get it all together. And the assembly was horrendous. They found that if they took half a dozen parts and put them in and then tried to crank the engine, it would just jam. So they'd have to take the parts they just put in out one by one until they found the one that was jamming. And then they'd file and adjust it. And I think adjusting as a euphemism for the use of the hammer. So they finished up putting the parts in one by one, adjusting them to fit and turning the crank. It was also what's called a monolithic construction. By that I mean, there's no way of getting out a part in the middle. For example, if this piece here snapped, then everything up to the top here would have to be taken out, and possibly some of the adjacent pieces. The broken part replaced, and then everything put back exactly where it was and all adjusted all over again. Today, things like this would be built in sections, and the sections would be bolted together, so it would be fairly easy, or relatively easy, to repair something. The other problem they had is that turning this crank was quite difficult. And Babbage had anticipated that. So at the top of the columns, they had to go up and down with those sector wheels in. These columns had springs and a big bolt on top. And the idea was that the bolt would be tightened so the spring balanced out the weight of all the parts below. That way, the column was basically floating, maybe a little bit of tendency to fall down. And that way, the crank would be quite easy because you didn't have to lift the weight. You just have to push the stuff up a bit. That was very good, except when they put in some extra parts, say they got up to here in the construction, they want to assemble a few more parts. To get at them, you'd have to take off the top and the spring, put in the new parts, and then tension it up so the parts are balanced, and then check everything and take it apart if it didn't work, of course. So, as I said, it was an absolutely horrendous effort. And just as a little side point here, the crank at the side has a 4-to-1 reduction gear. Babbage didn't have that. He had the crank directly on the main shaft. The Science Museum thought it would be a bit too hard to turn, so they put in the 4-to-1 reduction, which I think was a very good idea for a number of reasons, including that cranking is kind of a constant thing. Everybody turns the crank at roughly the same speed. But because of the 4-to-1 reduction, the engine's actually running at a quarter of its design speed, which is very good because you can see how the thing works. And of course, there's much less wear and tear on the parts, which is also a very good thing. Now here they are, smiling, and enough of the machine is there that it's going to work. They haven't done the printer that's on the far left, or would be on the far left. They're all smiling, so I suspect this is the morning it was opened up to the public on the bicentennial. No, the printer was a problem. They'd literally run out of money and run out of time, and they only had half the machine. It needed another 4,000 parts to build the printer. Unfortunately, Nathan Myhrvold, co-founder of Microsoft, and also an accomplished chef, he stepped in and he donated £200,000 for the production of the printing part, as long as he could make a copy of the complete engine in California. And he did that. And it was in the California Science Museum for quite a period of time. Now I have a video here of the engine in California. And I've, again, like the other videos, I've extracted part of it because it's fairly long. But please use the link to, or Google it, look at the whole thing.
The crank is rotating a vertical shaft on which are a number of cams. These are wheels that are set off center. As they turn, they push rods in and out across the bottom of the machine. Other rods are rotated and are geared to columns on the machine. The addition is taking place here. And now you see the carry. When the unit's position goes from 9 to 0, it trips a lever that primes the tens position above. And the tens position above may also be at 9, so a carry triggers a carry upwards. So while it takes one long operation to add all 31 digits together, it takes 30 small, short operations to carry the carry right the way up from the unit's position up to the top of the machine. Here we see the printing section in work. The paper tape's printed, and now it's going to press the numbers into the stereotype mold beneath.
In 1831, the funding ran out. There was a year of arbitration. As a result, Babbage got the plans and Clement got the equipment and the jigs. I think Clement wanted the plans. I think Clement had some ideas of completing the engine and making a lot of money. The cost of the government was £17,000. Babbage also put in a few thousand of his own money. And 12,000, approximately, of the 25,000 parts were completed. That was most of the calculating section. And the small section, the 2,000 parts roughly, was assembled and working. There was a lot of discussion, shall we say, about whether the government would fund continually, whether the government would add additional funding to the project or not. And John Herschel, Babbage's friend, was put in charge of a committee at the Royal Society. And I think he did a very good job on it because he reduced the question of continuing to spend money on the machine to 3 headings. First, on the absolute utility of the machine, suppose it's completed. Second, on the total amount ultimately to be expended on it, as weighed in relation to the absolute utility of the machine and to the claims of other branches of science on the public purse and on the sum already laid out. Third, on the probability or certainty that its completion will be secured by the expenditure of such sums as government may consider itself justified in devoting to it. And we'll take these one at a time. The final cost and uncertainty in the estimates. And I've added one in here, the number of machines needed. I haven't seen this anywhere on the web or in any of the books I've read, but it's just an assumption that one machine is enough. But to produce the mathematical tables they wanted to produce, if a second or third machine was needed, it would have a phenomenal effect upon the cost. And of course, the utility of the machine. So starting with the final cost and uncertainty in the estimates. Well, the prototype proves that the design was correct. There's no problem there. And we know the cost of production because the actual cost of half the 25,000 parts was 17,000 to the government, a bit of Babbage's money, so I've rounded it up to £20,000. And so the other 4,000 parts would be the estimate another £20,000. But we have no idea of the cost of assembly of either the calculating section or the printer. And we know, but we do know, that the Science Museum had a lot of problems assembling the machine they had. And I had thought, well, we can look at the time the Science Museum staff spent on it, like man days or something, and just relate that back to the parts here and then double it because of the printing is about twice as many parts. And I realized that would be entirely unreasonable because I think the Science Museum got a very unfair idea of how difficult this would actually be to assemble. And I'll explain. And this is a simplified engineering drawing. This piece of metal is 2 inches wide. So the engineering drawing would say 2.000 plus or minus 0.002. the 2,000th of an inch being the tolerance of the errors range of the parts Clements had made. This means that a piece manufactured anywhere between 1.998 and 2.002 is acceptable. Anything else would have to go back and be redone. And we know that in the calculating section, there aren't very many unique parts, but each of those parts, the figure wheel, the sector wheel, the carry mechanism, etc., required 248 identical copies. So when the Science Museum contracted this out, the person that won this contract would have used CNC equipment, computer numerical control. After all, you needed 248 identical parts, so these machines are extremely good at making highly accurate copies. And these machines are programmed with what's called G-code. And G-code originated from the Second World War, when paper tape was punched up to cause numerical control machines to follow certain procedures and steps. The C in front of numerical control for computer numerical control simply means that instead of the paper tape, they used a computer to generate the G-code to run the machine. So in this case, the G-code would have said, make a cut across here, across the top, turn right, go down 2.000 inches, and then turn right and go back over to here. The G-code had no information at all about the tolerance, the 2/1000th of an inch tolerance. The reason is that the tolerance is the tolerance of the machine. You have no control over this. It's whatever it is. And it so happens that in the 1980s, these machines, the type that would be used by the contractor, they built parts well within 1/1000th of an inch tolerance. So I think the Science Museum had problems assembling parts made to within 1/1000th of an inch tolerance. Parts made by Clement to 2/1000ths of an inch tolerance will be way more difficult to assemble and cause a lot more filing and adjusting. And if the Science Museum had the incentive to be absolutely historically correct, they would have asked the contractor to take this G-code that was going to run 248 times, and they'd have them make 248 copies, each adjusted with random errors, so the resulting actual parts would be in the range 1.998 to 2.002. with a statistical distribution comparable to those found by the parts made by Clement. Now, I want to be quite clear here. I'm absolutely not being critical of the Doron Swade, the Science Museum, the contractors, or anybody else. There's absolutely no reason why they would have done this. And if they had done this, the project would have taken way longer and cost way more and likely would have never been finished. So I'm very pleased they didn't think of this. Now, I did write to the Science Museum. I sent them an email, and I was quite pleasantly surprised to get a response from Doron Swade. He said that the parts had been tested to make certain they were within tolerance, but the people who did the work are no longer with us, and he doesn't think there are any records available, and so he doesn't know how much the parts were actually within tolerance. Maybe they were well under 1/1000th of an inch tolerance. And he did say that I had a good point. So Herschel's second point, the number of machines needed. I went back to the video of the machine in California, and it takes about 5 seconds to turn the crank. And as I said, there's a 4-to-1 reduction gear. Babbage would have had the crank directly on the main shaft, so it would have taken about 5 seconds to compute the next line in the table of finite differences. So we can say approximately 5 seconds to produce a line in a table. And I did some rough estimates, adding in some allowance for changing those stereotype plates and some time to clean and lubricate the machine. Very rough estimates. And then I went back to my 1964 Engineer's Handbook, and the first 100 pages of that contain mathematical tables. And I figured that the main customer for the mathematical tables would be engineers. Scientists and others definitely an interest, but they don't have a lot of money, and there aren't as many of them as practicing engineers. And I figured to produce those tables in the handbook would take around a month. And the compound interest tables, which had to be done to 1 penny precision, possibly a couple of weeks. And as I said, these are very rough estimates. So a few months, you're finished. And once you're finished, you've got the stereotypes, you've made up the lead plates, you don't need to run the engine again. But there are other tables. There are the navigation tables, the nautical almanac. And because of the complex motion of the stars and planets, the tables were produced for every year. And the tables themselves are complicated. There's a page at the top, and there's a line in the table for every hour of the year. And I just exploded a bit below, which shows the sun and the moon, and the altitude and declination of the sun and the moon at the various times. And I really am not certain, so these estimates I'm even more uncertain about than the others, but take them as a rough estimate. And there are other tables. Edward Sang, a Scottish mathematician, had produced 47 volumes of tables with 7 to 28 digits. He spent over 20 years doing it, as he said, quote, of leisure with his 2 daughters. I have no idea what his daughters thought about this. But he produced logarithms to 7 digits. He produced logarithms of the first umpteen thousand primes to 28 digits. And he did other tables, trigonometry, and so on. And if we put these into the equations, we've got a couple of months to do the engineering handbook and the compound interest, 8 months to do Sang's volumes, and a couple of months to do the navigation tables. So I think one engine would have done the job. And even if my estimates are out, I'm only figuring it running 8 hours a day, 6 days a week. They could have run a second shift. I do have a caveat here, however, because what about breakdowns? Considering the complexity of taking the thing apart and putting it back, I could see some reason for producing a second machine, but I don't know. I can't really justify a second machine. So the third item was the utility of the machine. And I think utility can be expressed as the customers willing to pay for it. After all, someone's got to pay for the engine. It's initially the taxpayers, but eventually you want to get your investment back. So presumably people buying the tables will pay for it. Now, I thought, for many years, I thought that the real customers for any tables at all would be engineers. But scientists, of course, and bankers and so on would need them, bankers possibly with the compound interest tables. But it turns out I was wrong. I talked to a number of professional engineers I know, and they said, no, John, they said, it doesn't work like that. He said the engineers didn't want to have anything to do with these tables because they had well-used graphical methods of doing these things, which would, of course, have been based on the original Greek geometry. And what did surprise me is that the tables de Prunier in France and de Sang in Scotland were never printed. Sang ran ads of a newspaper. It is proposed to publish by subscription a table of 9 place logarithms for the price of 1 guinea per part. He didn't get any takers. The tables existed, so why make new ones? Dionysius Larder wrote in 1834 that a random selection of 40 volumes of tables contained no fewer than 3,700 known errors. How did he know there were errors? Well, at that time, an error would be reported, and they wouldn't print a new set of tables. What they did was print an errata sheet, and they got distributed. And by 1934, there were 3,700 erratas, and at some point there were 4 deep. In other words, an errata to an errata to an errata to an errata. So the emphasis switched to errors. And somebody wrote to the Admiralty, every error is a shipwreck. Well, that got a lot of coverage because, after all, we don't want shipwrecks. I don't buy it. The nautical tables need a sextant and a timepiece, and you can only use the sextant when you can see the horizon. So you can't use a sextant near shore. And shipwrecks occur when ships hit a rock, and rocks are invariably close to shore. A ship could be wrecked because of a storm, but then where you are doesn't matter. The errors in the nautical tables don't cause storms. And in terms of rocks, there is an exception to what I said. There's a very large rock, 3 miles by 2 miles, called Fair Isle. It's stuck in the middle between the Shetlands and the Orkneys. You can see it from the north of the Orkneys on a clear day. And it's been inhabited for years, hundreds of years, and all the fishermen and trading people and so on up there would know about it. It wasn't surveyed until 1839, and even then it took 20 years to get the survey published on the nautical charts. My question of the Admiralty is, why, a couple of hundred years ago before Babbage, didn't they put a dotted line and a big circle around roughly where Fair Isle is, a warning to stay clear? That would have saved more shipwrecks than all the errors in the nautical tables. And these errors, well, I'm talking about typical errors in commercial operations. I'm not talking about military or scientific operations where it's a bit different. Other errors would have occurred because of the typesetting and the proofreading, both of which were exceptionally boring jobs. And it must be bad enough to typeset and proofread a novel, but doing it with digits, thousands and thousands of digits, day in, day out, would be horrendous. I think the only advantage of proofreading would be you might be able to sit down. Another source of error was the printing press. The digits, little bits of lead, were put together in a frame and clamped up and rubbed with ink and pressed down onto the paper. The ink they used was fairly sticky, so sometimes they'd pull the plate up and some of the lead type would fall out. It was up to the printer to put them back, and of course they made mistakes. And there are examples of tables printed where one print run, a part of the run is all correct, and then part of the run has the same error. And the error is a substitution of 2 digits. For example, a 6 might be switched with a 5, easy enough for the printer to do. But what are the results or consequences of these errors? Well, if it's in the first or second digit, it's going to be obvious to any user. It's the second or third digit. Well, it does depend. But the example of sailing and navigation, any navigator knows roughly where they are. So if there's an error in the table, it would be fairly apparent because they'd be, well, possibly in the middle of the Sahara Desert instead of the middle of the Atlantic. So it would be kind of obvious. But even a small error would be noticed, and the user could check the numbers because they're all in numeric sequence. So if a number doesn't fall in sequence between the adjacent numbers, it raises a flag. So I don't think that these errors are quite as serious as suggested, as I say, with the exception of scientific and possibly military use. But then if those uses were really critical, the government could have said, okay, guys, we need these tables. We have to have them. We will fund them regardless of the usability. You see, I don't think in 1821, Babbage went to the government and asked for £17,000 to spend over the next 10 years making half the parts, and then he'd be back asking for another £17,000 so we could come back after 20 years, another 10 years, for more money for the assembly. I suspect that in 1831, he was at least 6 years behind the schedule and at least 3 times over budget. Interestingly, Babbage received a letter from one of the workmen. It said, in effect, the inventor's incentive is to get the invention built. The builder's incentive is to keep working as long as possible. And in this case, when the Science Museum tested the measurements of the parts made by Clements, they found things like a support column. But the only thing about a support column that's important is its height. There are little termed moldings at the side to make it look pretty. As long as they look similar to the other moldings, it doesn't matter. And they found that those moldings were all done to within 2/1000th of an inch tolerance. So I think there was a certain amount of overbuilding going on. And if we go back to the space where space telescope, large projects using technologies are late and they are over budget. And the James Webb Space Telescope cost around $10 billion. It was about 10 years late and about 10 times over budget. Now, fortunately, it was funded and its utility was justified. But I don't think the utility was there from the difference engine to justify the great expenditure. And I think it could well have been 10 years late. Well, I think it could have been 20 or 30 years late. And it could have been 10 times over budget easily. It was a failure. The failure stopped anyone else building calculating machines. The next major advance was in the year 1880 in America. The cost of £17,000 in 1830. What is that in today's money? Well, there are some estimates on the web. I don't necessarily agree with them because one estimate says that £17,000 will buy 2 battleships. And at that time, Babbage had just inherited £100,000 from his father, who was a banker. I can't imagine that a banker could accumulate enough money to buy a veritable navy of about 20 battleships. And another website suggests that in today's money, it was like Google and Apple combining their resources for a 10-year project. And again, I don't believe any banker today could buy Google and Apple for 10 years. So I'm just going to say it's a lot of money. I think it's a bit like the Concorde. Great piece of engineering, but no market, no customers. And I'm quite sympathetic to the Prime Minister, Robert Peel, who said, "What shall we do to get rid of Mr. Babbage and his calculating machine?" So the first automatic calculator was purchased by the government, funded by £17,000. And the failure stopped anybody else building calculating machines. The Schwartz brothers, George Schwartz was a Swedish printer, had read about the difference engine project in a newspaper, not a scientific journal, so he had no idea about how it worked. He just knew basically what it did. So he and his brother set out and made one. They brought it over to England and they sold it to the Dudley Observatory, who printed life tables. And it did work. It jammed up sometimes, probably the result of not a very good locking mechanism. But it did work. And in a normal world, it would have generated interest. Investors would have come in, and Schwartz and others would have improved on the design, fixed the locking problem, and it would have been developed, and all would be good. But no investor was going to go near anything with the word calculating in it. So they went back home, and that was it. Another Swedish chap, Martin Babbage, he built this machine to print logarithm and interest tables in 1860. I have no idea how it worked in such a small space. It would be interesting to find out. But he didn't get anywhere. Nobody was interested in talking to him. It wasn't until Doron Swade, on US Thanksgiving holidays of 1884, he went down to his local grocery store. He picked up a used macaroni box, I think it's a wooden box, skewers, staples, rubber bands, and cardboard. And in a couple of months, he produced a prototype. And it was worked sufficiently that he could demonstrate it. And he got investors, and he started a comptometer company. And things set off in the States, the building of mechanical calculators. It became big business. So what about difference engine 1? Well, first of all, why 30 digits? 20 digits will count the grains of sand in the Sahara. And why 8 columns? We did our tables of logarithms with 2 columns. We probably need a few more to be sensible, but still, you don't need 8. And why all that complexity in the printer? Babbage could have made a stereotype which just copied what was on the paper tape. Forget about multiple columns. You can stack these lead plates together side by side. You can put in the headings and the page numbers manually. You don't have to do any proofreading. And the only typesetting is just the headings and the page numbers. So it'd be so simple and way, way simpler. So in my opinion, a difference engine light with maybe 5 or 6 columns and perhaps 12 digits, it would need about a quarter of the parts. And remarkably, he had the parts. He had 12,000 parts. And the assembly, which I think would have been quite difficult with Babbage's parts. But if you had only using a quarter of the parts, you can choose the ones that fit. You can go through and sort them into oversize and undersize, and you wouldn't have to do much filing or adjusting. You could get the thing up and working. And he had the parts. He could have funded a simpler printer. After all, he did have £100,000. Maybe a quarter of that would be enough to do the assembly and make the simple printer. Once that was in place, he'd immediately generate some credibility, immediately get investors, and a lot of interest. So why didn't he? I really don't know. He might have been stubborn. He might have lost interest. Maybe he was only concerned with the intellectual challenge of inventions. Who knows? Anyway, after the Science Museum built the thing, there was a lot of interest, and amateurs and students and so on made models. This particular one is made in Meccano. It has 5 columns and I don't know how many digits. But I want to point out here that this section below isn't part of the figure wheels and the sector wheels. It's all the mechanism to make the sector wheels go up and down and the various things rotate. It's even more complicated than the area where the data is stored and the arithmetic takes place. Here's another one made by Lego. And the one I particularly like is made by the Royal Holloway College in London, and it's operated by steam. And I particularly like it for that reason, and it's built oversized. So not only can you see the parts easily, but it's also, so to speak, blown up. Things are further apart in this machine than in real machine. So you can see how things work. And I'm going to play a small section of the video that's available on the web. And I do advise you to watch the second half, because the second half, they show you how the machine is set up to calculate a simple polynomial. Next week, we're going to talk about Charles Babbage, Ada Lovelace, and the times they lived in. And we'll be going to one of Babbage's famous dinner parties.